So now in the past two lectures, we have been talking about integrators and differentiators, how to understand the step responses and pulse response of integrators and differentiators. In this lecture, uh, what we need to do is that we have to slowly start adding non-idealities to the integrators, starting from finite gain, saturation limits, and maybe, if time permits, bandwidth. Once I start adding all these three non-idealities, how does this response, the pulse response and the step response, deviate from their ideal expected behaviors? So that's what we wanted to study in the series of lectures. And I felt this is very important because this forms the foundations for circuit design. If you understood this, see, most of advanced circuit design concepts like data converters and amplifier design and all of that expects a good understanding of how those systems behave under different conditions. So a step input is like a sudden transient input at t equal to 0. And once it flattens out, that's like a steady state response. So if you understood how it behaves for this, and for both from a time domain and frequency domain point of view, then it's really helpful in understanding even complex systems. So that's why I'm spending more lectures than what is needed, but the reason behind is that. So let's start with a simple, quick refreshing. I'll quickly refresh first order RC circuits. If I take a simple first order RC circuit, you know that if I feed a positive step, then it will have a first order raise. So I'm calling this as a first order raise. It will asymptotically reach the steady state value. So it will start from an initial value and then eventually reach. So if I were to write a mathematical expression for this, it will be its initial value plus final value minus the initial value. V of infinity is the final value minus V of 0 times 1 minus e power t by tau. Okay. And everything here, the time constant, if you know the time constant, then you know everything about a first order system. Okay. And initial condition. If you know initial condition, you can guess what the final value is going to be for the system. And then if you know the time constant, then you can predict the response of the system. So if I feed a pulse input, this here, there is no steady state output here because the input keeps on changing. It goes from 1 to 0, 1 to 0, and so on. And so in such a response, your output will also keep oscillating between two values. What I'm interested in is what is the shape of the waveform? How will that shape look like? Given I know some relationship between the time period of the signal or the frequency, the fundamental frequency of the signal, F naught be the fundamental frequency. So fundamental frequency of the signal is the minimum frequency of a periodic signal. It will contain fundamental and harmonics of the fundamental, multiples of fundamental. Okay. And if you know relationship between the fundamental frequency and or the fundamental time period and the time constant of the first order system, if you know these two, relationship between these two, can you guess the waveform? Okay. After a point, especially when you're circuit designers, you will be simulating more than transistor circuits which will involve more than 4 or 5 transistors. Once you start analyzing complex systems, you will not be able to do a hand analysis. It will become too complicated to do a small and derive some clean results. What you need to then rely on is intuitions. Okay, you have to understand, you will get an output and you should be able to make sense of the output. Okay, does that output make sense? And how do you make sense of those outputs? By understanding small reduced systems, systems which are much simpler to analyze. We understand them very well, very deeply. And then based on that understanding, we try to understand more complex systems. Okay. So that's why understanding first order is very useful. So we know if I feed a step input, you know that it's going to have a first order raise. If you look at a pulse signal, locally it can look like a step input near these rising edges. If I make this assumption, the time period is much, much greater than the time constant. Then what does it mean is that for this RC circuit, the capacitor takes the RC time constant is much smaller than the time period. It means that you can charge your capacitance in a time much smaller than the time period of the signal. That's what it means. Smaller time constant for a first order system. For a circuit designer, it simply means that you can charge your capacitor much faster. So if I feed a sudden step input, your output will quickly raise to the final value. So if this is half of your clock cycle, and if half your clock cycle is greater than 5 time constants, then obviously it will say the output would have settled to its final value. So if you're going to feed a step that goes from 0 to V peak, then the final value is V peak, initial value is 0, and the system would have settled to V peak within half a clock cycle. Now suddenly now the capacitor has a voltage of V peak at the end of the first half clock cycle. In the next half clock cycle, the input suddenly goes to 0. Now the final value for the output is 0 because the input has gone to 0. It starts from an initial voltage of V peak and it will decay down like this. It will decay down and reach 0. That's the final value. And then the process will repeat endlessly. Okay, it will keep doing this. So if you just plot these waveforms on an oscilloscope, provided this condition is met where your time period is much greater than the time constant, you will see a waveform which looks nearly like a square wave, but near the edges, you'll see a first order rise and first order fall. Okay, and I gave you an example where you will see this. You will see this in if you ever get a chance to build, maybe as an engineers, you go on to build, for example, anytime, right? The big inventions drive a lot of jobs. So now the big thing is artificial intelligence. So a lot of engineering goes into building the hardware. So if you see the data centers, it contains a wide range of chips, from processors, the connectors, from machine to machine. If you want to do distributed computing, then data has to flow from machine to machine. Now, hardware guys, we become the limit on how fast the data can flow. Okay, so in such systems, when you look at the bit streams, when you transmit these digital bits into those wires, you will see some kind of waveforms like this. It will be, in fact, much more attenuated versions. You will not even see such sharp edges. You will see some waveforms that looks like this. Okay, and that I'm trying to say that if you understood first order system, those waveforms should make sense to you. What's actually happening in the system? If the waveforms look like this, wherein the steady state value is attained within a single period, then you know that I've told you that time constant is much smaller. Now start thinking in terms of frequency. This RC low pass, an RC first order system can be seen as a first order low pass filter. So it can be seen as a system with a finite bandwidth. Okay, it means that it will pass a certain range of frequencies without any attenuation, and signals that are outside the bandwidth will face attenuation. Okay, so you can say that if you see a waveform like this, if you see a waveform which is getting charged to full its final value and then decaying back again to its final value, what can you say in terms of frequency? Let F naught be the fundamental frequency, and the bandwidth of the system, let's call it FBW, is the bandwidth of this RC circuit, which will turn out to be 1 by 2 pi RC. Okay, what can you say in terms of frequency and bandwidth? You just look at a waveform like this, and what inference can you draw? Can you say something about whether the bandwidth is lower or higher? So you know this information, time in terms of time periods and time constants. I'm saying, can you think about it in terms of frequency? The waveform is looking like this. It's almost looking like a pulse signal, which means no. Forget about frequency into bandwidth being constant. See, you have a system like this, with some transfer function, and you're passing an input signal, a pulse signal. The output of this system looks like this. It looks like a first order charging and this. it looks nearly the same, right? It's almost the same. It looks close to the waveform, except there is some smoothing of the edges. So which means more or less it is transmitting this waveform as it is. So can I say it is passing the signal as it is? If it is passing the signal as it is, I'm just saying in terms of bandwidth, how can you say that? What can I say about the bandwidth of the system compared to the input signal frequency? Can I say the bandwidth is much greater than the input? See, if for a low pass filter, if your bandwidth is much greater than the input, then it will pass the signal as it is. So that's what is happening. So when you see a waveform like this, which is rising to its full value and falling back, rising it to its full value and then falling back to zero, immediately you should know, okay, this is a high bandwidth system. Okay. So you don't have to worry that, okay, these systems may not suffer much from ISI, problems like ISI. So that's the understanding you gain by looking at this waveform. Now we'll analyze the second more extreme case. What if your time period is much smaller than the time constant? Okay, time constant is a measure of how fast the system charges the capacitor. I'm saying that the time constant now is much greater than your input signal's time period. So what do you think the waveform will look like? Here we can draw a wide set of intuitions. Yeah, so it won't reach the highest value. That's right. So it won't reach the, because it won't get time to reach the highest value, it'll do something like this. Okay, it won't even get time to reach the peak value. It will do something, it will go to a lower value. Now, can you tell me, if I measure the DC average value of this waveform, what will be the DC average value at the output? This is a simple first order RC circuit. See, eventually you know that, okay, the waveform is going to go through some kind of, I'm using the word ripple. It's going to go through some kind of oscillation around some mean value, steady state, What do you think that mean value? What will be the DC value? Assume that your input signal goes from 0 to V peak with a 50% duty cycle, which means it's on for T/2 and off for T/2 seconds. What will be the DC value at the output? The average value at the output here? No, what is the DC gain of an RC filter? What is the DC gain? If you plot its frequency response as a function of gain, as a function of frequency, 1, right? The DC gain is just 1. Which means, what does that mean? Whatever is your input DC value, output DC value has to be exactly the same as the input DC value. The DC gain is just 1. For a low pass filter, 1 by j omega RC, take magnitude square, magnitude, it will be 1 by root of omega RC the whole square. Omega equals to 0, you get 1. So which means input DC has to be exactly equal to the output DC. So yes, you are going to get some waveform that will look like this, that will look like a first order RC charging, but it won't fully reach its steady state. But if I measure its average value, okay, you can measure average values on oscilloscopes, or let's say you're able to read this data on some software. On MATLAB, MATLAB, you can even read it through Python. There are a lot of softwares with which you can read hardware data. If you're reading this hardware data, and you can then do all post-processing on software. When you do that, if you know that, okay, to make sense of this system, because it's a very simple low-pass system, the DC average value will be exactly equal to the input DC average. So this DC average, what do you think will be this value at the output waveform? Given that input signal is looking like this, Vp by 2, right? This will be Vp by 2. Now let me give you a much simpler explanation for this. Okay, how do you know? By looking at the waveform. If I tell you that this is the 3 dB bandwidth of this RC filter, which is 1 by 2 pi RC in Hertz units, in radians per second unit, it's going to be omega bandwidth will be 1 by RC, radians per second. If I tell you that the fundamental frequency, see, it's a pulse signal, right? If it's a square pulse signal, it will only contain odd harmonics. If the duty cycle is 50%, a square pulse signal will only contain odd harmonics. And I gave you an intuitive reasoning for it. If you remove the DC component out, you can always find within one single period, one point around which the function will exhibit odd symmetry. Meaning it will obey this property, f of t equals minus of f of minus t. Okay, if you cut this waveform in one unit interval, one time period, you can always find some point in this waveform around which the function will exhibit odd symmetry. If it does that, then you know the function can only contain odd harmonic. It's a purely odd function. Therefore, it will only contain odd harmonics. I'm just removing DC out. Once I remove DC out, I can figure, or even if you have DC, I can still find out some point around which the odd symmetry can be exhibited, can be observed in this function. Now come back to this. Now you know all the harmonics are odd harmonics. Let's assume your bandwidth is here. The first harmonic is F naught. Second harmonic is somewhere here. Third, 3F naught and so on. Which means I'm assuming here the fundamental frequency here is much greater than the bandwidth of the system. This is what I'm expressing this relationship in frequency domain. Otherwise, I can say something like this, 1 by t. If I inverse the time, your time period is much smaller than time period indicates 1 by f naught is much smaller than the RC time constant. On frequency domain, it looks like this. Can you tell me, if you look at this graph, at frequencies much greater than f bandwidth, what shape does this resemble? I mean, what does this shape remind you of? It's falling off at some rate, at 20 decibels per decade. What does it remind you of? We have seen integrators, differentiators. Does it remind you of something? The transfer function in this region? After f bandwidth, if you are to just look at this transfer function from this point, you are looking at a graph which is falling off at the rate of 20 decibels per decade. So it is 1 by 1 plus SRC. If your frequency is much greater than 1 by RC, I can approximate this to 1 by SRC. So what does this remind you of in this region? An integrator, right? It reminds us an integrator. So if I take an ideal integrator, it will look something like this. It will blow up to infinity. But if your signal contains frequencies only greater than f naught, then as far as the signal harmonics are concerned, frequency f naught, 3f naught, and so on, they will think that this RC circuit is just an integrator. So we know the output of an integrator. If I feed this pulse signal to an integrator, if you remove the DC component out, I'm going to treat this signal like we did in last class. We split the signal into two parts. A DC component whose value is B peak by 2. Once you remove this DC component out, you will be left with a signal which oscillates between minus V peak by 2 and plus V peak by 2. The time period still remains the same. If I feed a signal like this, if I feed this signal, a pulse signal with zero average value that goes from minus Vp by 2 to plus Vp by 2 to an integrator, what should I expect? What kind of an output should I expect? It will be a ramp. Okay. So if your fundamental frequency of your input signal, this periodic pulse signal, is much greater than 1 by 2 pi RC, or the bandwidth of this RC low pass filter, then you can treat it like as though the RC low pass filter is going to behave like a pure integrator. And you should see almost a ramp kind of a response like this. It's just going to integrate this waveform. When it integrates this waveform, when you start from a negative value, it will go to reach a peak, and then it will come back to zero, right? It will come back to zero like this. It will reach a peak, come back to zero, reach a peak, come back to zero, and so on. Because whatever it integrates in the positive half cycle, it loses all of that in the negative half cycle. So then it returns back to its initial value. Okay, that's what you should expect if your bandwidth is much greater, if your bandwidth is much lesser than the input signal's frequency. Okay, it will almost look like a ramp signal, and which means, or otherwise, I can say that the RC circuit will act like an integrator. Okay, you can use this as a cheap integrator. If you know that your input signals doesn't contain any DC content, then you can use a simple RC circuit as an integrator. So if you guys, I mean, why I'm saying this is because when I first, we used to have this assignments in ComSys, communication systems. I didn't do the course, but my friends used to do it. I'm an E&I student. So what used to happen is that the lab, I mean, the one of the lab experiments that we, I mean, I used to just sometimes help in building experiments. We used to use this for, there is something called matched filter receivers and all that. If you guys have studied, we used to use simple RC circuit for integrator. First, I saw some book first time when I read it, they were using an RC circuit as an integrator. This was my third year first sem time. So then it made sense afterwards. Why was that the case? Okay. Because it took me some more time in 3.2 to understand when we built an experiment. Okay, then you see, okay, it actually integrates. If you choose your bandwidth to be much smaller than the input signal frequency. Okay, you didn't need to put an op-amp based integrator. We will see later. If you want an op-amp based integrator, you have to worry about stability. You need to have an op-amp IC first of all. Here you don't need it. You just take two passive components and they act like integrators. Okay, under certain conditions. What is the condition? The input signal frequency you're feeding should be much greater than the bandwidth of this RC filter. Okay. Okay. How are you saying that the output will have an average value of Vp by 2? See, that I'm starting, see, eventually you have to understand there is, what we are looking at is steady state. See, when you look at the frequency response graph, the information you can gather from a frequency response graph is usually the steady state behavior. Okay. So if it tells you the DC gain is 1, you should look at the steady state. If you feed a DC signal, the output DC gain will also be 1. Okay. So since the DC gain is unity, here the DC gain is unity. What does DC gain of unity mean? See, okay, first of all, what does frequency response mean? If you are given the frequency response of a low pass filter like this, it tells you that if I feed a sinusoid of some frequency omega, okay, if I feed a sinusoid of some frequency with an amplitude A, then by looking at the frequency response, I can precisely tell what will be the magnitude of the sinusoid at the output and the phase. So I've shown only magnitude response. You need to have the phase response as well. So your frequency response, h of j omega, is actually a complex number. Anytime you talk about complex numbers, a complex number will have both magnitude and phase, right? It's a real and imaginary part. I can express it in terms of polar coordinates. So you will have some magnitude, let's call that r, and then there will be some phase. The r tells you the frequency, the magnitude of the frequency response tells you the amplitude of this sine wave, the factor by which the amplitude of the sine wave will get scaled at the output of this system. So if I feed a sinusoid of some frequency omega, by looking at the frequency response graph, I can say that what will happen to my input amplitude when I look at the output. So if let's say the gain at this point is say h of, let's call this frequency as some omega 1, h of j omega 1, then my output sinusoid, input sinusoid's amplitude is A, output sinusoid's amplitude is going to be h of j omega 1 times cos omega naught t, cos omega 1t. And I can also predict the phase. The phase of this output sinusoid will be given by, if you find the phase, that will be the angle of h of j omega 1. Okay. So that's why frequency response is a very powerful tool. By looking at it, you can predict how will the system behave if I feed different sinusoids of different frequencies. So DC signal is a sinusoid of 0 frequency. Okay, so which means it's going to be constant all the time. Okay, so I can represent sinusoids using complex numbers. How do you represent a e power j omega 1 t? So this is a complex sinusoid of frequency omega 1 and amplitude a. Okay, now if I make omega 1 equal to 0, if omega 1 becomes equal to 0, then the sinusoid will reduce to a, which is nothing but a constant. That's a DC input. So if I feed a DC input to this system, then the output is going to be equal to, frequency will remain the same. The output will be equal to a times mod of h of j omega 1 times e power j omega 1 t plus 5. Okay, so I think I'll erase it here and then. So am I missing something? Is this is what you're asking, or is there something else that you're trying to ask here? Or am I, is you are aware of all this, right? What I just said, what is frequency response? Are you aware of that, or you want me to explain that part? Oh, okay. I get it. Okay. So this part is clear, right? So I mean, I'll come to that. So the what? Yes. So what you're asking here is that, okay, I'm sorry. So the frequency domain understanding part is clear. So one of you're asking that, okay, if you look at this waveform at the output, the waveform doesn't get a chance to reach VP at all. Okay. It's going in this way because assuming your time period is much greater than the time constant, it would take really a very long time to reach V peak. But this waveform doesn't even get the chance to reach V peak. It's only reaching a peak value. What is this peak value? I can treat it like an integrator. Then I'll say V peak by RC into T by 2. That will be the peak value it will go to. That's what it will go to. So that will be given by V peak by 2 into T by RC. And we just said this T is much, okay, T is much less than RC. Your time period is much smaller than the RC time constant. So since T is much smaller than RC, if you look at it, in a single cycle, it is never getting to fully charge to V peak at all. It's charging to a very small fraction of V peak by 2. Then I just explained using frequency response analysis that the DC value at the output, VO of, if I write V of j omega at omega equal to 0, that's the DC value, will be the same as the DC value at the input. Okay, Vi of j omega at omega equal to 0. And this follows from the fact that the DC gain is 1. How is the circuit actually reaching this DC value? But which means the DC output DC value should be V peak by 2. How is this reaching? If we are not even giving it this time to charge, that capacitor is never even getting charged to V peak. So that you can explain by thinking like this. Okay, that I understood the question. Let me just explain this way. So think like this. If you recall from my previous explanations, I said that you can treat it like an integrator. How does an integrator behave if I feed a signal that looks like this? If I feed a signal, let's say that goes from Vp by 2 plus Vp by 2, the on period is T by 2 and T by 2, and I'm going to feed a DC component whose value is V peak by 2 plus this. I'm feeding two inputs to an integrator with some time constant, 1 by RC. This guy, if I feed this guy, that's going to lead to what is this going to lead to? This is going to lead to a response that looks like this. It will lead to a triangular response that looks like this. What will happen if I feed Vp by 2 to this first order RC circuit, a step input of say 0 to Vp by 2, if to a first order RC circuit, it will take a really long time to charge. Yeah, it will look like a ramp near the origin, but eventually it will settle down to final ramp. So what will happen in this circuit is that, what will happen to this circuit? is that it'll take a really long time to charge up. See, it's going to be a ramp, but it will also have a linear component riding on top of it. It will be a ramp because due to this, it will be a ramp. And due to this linear component, there will be a linear, due to this DC component, there will be a linear component which will slowly increase this. But remember, this is not an ideal integrator. RC circuit is not, it is actually what? It is a first order system, which means if I feed a DC input of value Vp by 2, that's like a step input, 0 to Vp by 2, your system will respond like this. It will try to do a first order charging, meaning it will look like a linear response near the origin. And after that, it will slowly start saturating. So after several time constants, 5 RC time constants, you will reach the output capacitor will be charged to Vp by 2. Okay, after several time constants, it will be charged to Vp by 2. So what you will see is that you will see a ramp signal like this. You will see a triangular waveform like this. And in the steady state, you will see, the capacitor will be charged to V peak by 2. And on top of it, you will have a small triangular waveform riding on top of it. This won't be V peak by 2. I mean, this will be much smaller. This peak amplitude will be how much? You can predict it, right? V peak by RC into T by 2. So that will be the peak that it will go to. So you'll have a DC peak of Vp by 2. On top of it, you'll have a ramp going back and forth. And this ramp is because of the high frequency component. Okay, yes, this, if you measure its peak to peak, it will be much smaller than V peak by 2. This peak to peak will be much smaller because it never gets to fully charge in a single cycle. But you should keep in mind the DC content of the input is slowly charging your capacitor. So your capacitor on every cycle, it is going through this, positive, negative charging due to this high frequency signal. It is also getting small incremental charges every cycle from the DC signal. The DC signal is slowly dumping some incremental charges, which is what is leading to this ramp rise. But since it's for ideal integrator, it will just blow up to infinity. I mean, there will be a ripple, but it will keep on doing this. But this RC circuit there is a word that is used in popular literature called lossy integrator, which means it's not ideal. Okay, DC gain flattens out and the DC gain is equal to 1. So since it flattens out, so since it flattens out, it will reach a finite value of Vp by 2. So one of you are asking, so the ramp will be added to regular first order step output, regular first order ramp output. Yes. See, we took this signal, a pulse signal, which goes from 0 to Vp and 0 to Vp. And we said we can split the signal as 2 components, DC plus a signal with 0 average. And then I'm going to apply principle of superposition and then say that I'll first find the response for this and find the response for this and add the 2 responses. For the pulse response, it is a ramp. It's a ramp like this. And one of you rightly pointed out that because it's a pulse signal which is going from a negative to positive value, it will never reach V peak. It will be a very small, this peak to peak variations will be much smaller than V peak. Okay, it will be much smaller than V peak. But the DC component, which can be again treated as a step input, which goes from 0 to V peak by 2, that guy will slowly add charge to the capacitor. So yes, output will be sum of 2 components, ramp plus a periodic sawtooth signal plus a ramp signal. You add these two, that will be the resulting output at the first order RC circuit. In fact, I shouldn't use the word ramp here. Remember, what will this be? I mean, will it be a ramp or what kind of a waveform will that be? It's a first order charging. So it's not a ramp. It will look like a ramp when you're a fraction of a time constant. See, this is one time constant. If your one time constant is 60%, let's say your less than 10% of the signal's peak value. So this is the peak value, Vp by 2, and your 0.1 times Vp by 2. You are just with less than 1%, 10% of your peak value. In that region, the ramp, this function will look like a linear ramp. After that, it's just an exponential approximation. 1 minus e power minus t upon tau will be approximately equal to t upon tau. If t by tau is much less than 1 or t is much less than tau. So which means if the time interval of interest where you're observing should be much smaller than the time constant of the system. In that region, it will look like a ramp. But if you start looking at it after the one time constant, it will slowly start asymptotically reaching the final value. It will be a first order response. So what you should expect something like this. If you were to plot this, if you were to simulate this from t equal to 0, assuming 0 initial capacitor voltage on the capacitor, it will look something like this. You should first draw a first order RC circuit waveform whose peak value will be Vp by 2. On top of it, you will have this kind of a response. Okay, because I'm just maintaining the average value is Vp by 2. So you will see a response like this. Okay, this is how you will see. What I showed you guys is the steady state response. Steady state, it would have reached Vp by 2, and it will keep oscillating between two values. That's it. So to keep in mind, to just quickly summarize, you can just predict by looking at the output waveform of a first order system. But if you see the output waveform looks like a triangular waveform, okay, then you know that the bandwidth, you are severely bandwidth limited, meaning your bandwidth of this first order RC circuit is much lower than your input signal's frequency. Severe ISI, right? There is a lot of ISI. Your signal is not even going through, it's not going to go through full charging. Okay. So you can say that this is almost like a ripple on some DC average value. So that clearly tells you that, okay, your bandwidth is much lower. If you see a proper full charging within a single cycle, a waveform that looks like this, then you know clearly that it's a wide bandwidth filter, which means all the frequencies have been passed through this. So there is no issue there. So here it's a behavior of an integrator. For this ramp signal, it's behaving like an integrator. And for this DC signal, it's behaving like a first order circuit. So this is how it will look like the steady state for a first order RC circuit. So we'll come back to this. So if you take a first order high pass filter, which is again a cap at the input and resistor at the output, we analyzed this circuit in the previous lecture, and we said if you meet this condition, which means your time period is much greater than the RC time constant. So first, the moment you apply a step, output will quickly reach V peak, and then it will go through a discharge. Output will then be discharged to 0. What's actually happening is your capacitor is getting charged to V peak. Okay, so it will discharge like this, and when you apply 0, output voltage will be at minus V peak. And why is that? Your capacitor is by now charged to V peak at the end of half clock cycle, and when you make the input go to 0, the voltage at this output will become minus V peak at T by 2. And then again, it will get discharged. The resistor will discharge this capacitor. And if your time constant is much smaller than the time period, then it will quickly discharge it. So it looks nearly like a differentiator. And this, I think, since you guys must have already built differentiators, circuits in your labs, you must have seen this waveform when you fed a pulse input. Okay. This is something you'll observe if your time period is much greater than RC. Okay. Now, let's try and explain this using frequency response. What is the transfer function of SRC by 1 plus SRC? A high pass filter, that is SRC by 1 plus SRC. If you try to plot this transfer function, it's going to look something like this. It will be 0 at DC. See, on a log scale, whenever I'm plotting on a log scale, 0 corresponds to minus infinity. That's like 10 power minus infinity. So I'm on this axis, I'm plotting quantities in powers of 10. So 10 power 0 is 1. So 0 decibels is like 1, and 10 power minus infinity. So this will be at minus infinity. A high pass filter, after a point, it will reach a flat value of 0. This will be 0 decibels. And the point where it transitions to a flat region is your bandwidth of this high pass filter, which is equal to 1 by RC. Now, this condition, T much greater than RC, which means your time constant is very fast. In frequency domain, it translates to, so this is your F bandwidth, omega bandwidth. So if I write it as 2 pi, this will be F bandwidth. Your bandwidth of your filter, this is your 3 dB bandwidth, is much smaller than, is it smaller or I think it's greater? Yeah. Your bandwidth is much greater than your input signal's fundamental frequency. That's what this means. Your time period, if I say your time period is much greater than RC, which means your time constant is very small. Small time constant, large bandwidth. Bandwidth is inverse of time constant. So this translates to your F bandwidth to be much greater than 1 by T, which is F naught. Which means in this region, your input signal will appear somewhere here. So this is your F naught. I mean, let's assume F naught is somewhere here. F naught, 3, F naught, and so on. F naught will be in this region. In the region that I've circled, what does this remind you of? If you just look at this response, what does that remind you of? What kind of a response does it look like in this region? It's just linearly, yeah. One of you said that. Can you guys think? It's increasing linearly. So look, start from this transfer function. SRC by 1 plus SRC. Differentiator, right? So if you assume that SRC is very small, which means your 1 by your at frequency is much smaller than 1 by SRC, it approximates to, at frequency is smaller than 1 by RC, it approximates to SRC. So that's like a first order differentiator. So therefore, if you look at a waveform like this, you know that it's actually properly differentiating it. What is the DC average of this waveform? It's going from minus VP to plus VP. What is the DC value of this waveform? 0, right? Positive and its negative cycles are fully cancelling out. So DC average is 0. And that makes sense because for a high pass filter, the DC gain is 0. For a high pass filter, I'm calling HP as a first order high pass filter. J omega at omega equal to 0. The DC gain is simply 0. So even if your input DC is finite, output DC will be 0. Okay. So this is the kind of waveform you should get when you look at the output. Then you can clearly see it's behaving like a true differentiator. It's differentiating the input signal. Okay. Now we'll analyze the second case. So I gave an explanation from frequency domain as well. If you look at this frequency plot, that's what it tells you. It tells you that in this region, when your input signal is much lower than the bandwidth of your high pass filter, the high pass filter will simply act like a first order high pass filter. It will simply act like a first order differentiator. It will just differentiate it once. And it makes sense, right? The derivative of the signal in this region is negative. So that's why it goes from minus V peak and plus V peak. Remember, an ideal differentiator, the high frequency gain of an ideal differentiator is infinity. If you see that, ideal differentiator just goes to infinity. So that's why you will normally see impulses if you pass the signal through ideal differentiator. But then here, if you observe this waveform, this is reaching a maximum value of the peak value is reaching. That's the same as the input peak. Okay. And that follows from the fact that the high frequency gain of first order high pass filter is 1 or 0 decibels. So the sudden change in the output cannot exceed the change in the input. If your input changes by VP amount, then the output can at max change by the same VP units, VP by the same change, VP volts. So that follows from the fact that the high frequency gain is in 1. The infinite frequency gain is 1. So even though there is a sudden step, I said that locally you can treat in this region the as though it's like an infinite frequency sinusoid. So suddenly it's jumping to V peak. So if I want to find what is the value that the signal will take, I need to look at the gain at the infinite frequencies. Hp of j omega at omega equals infinity. This gain is 1. So the maximum step change in the output, sudden step change in the output, can never exceed the sudden step changes in the input because of it follows from the unity gain from a frequency domain that's a frequency domain interpretation, which is why here you see, right, it's 1 V peak in the positive half cycle. When it goes from 0 to V peak, it's positive half cycle. Okay, in that positive half cycle, the maximum step jump is 1 Vp, right? 0 to Vp volts. In the negative or the falling edge, the signal goes from Vp to 0. So that's a delta change is minus Vp. That's the net negative change. And that's the same as the output signal's peak. So this, why are we getting minus Vp and plus Vp? This follows from the frequency domain graph. That follows from the fact that the DC gain cannot, the high frequency gain is just equal to 1. Okay. That simply states that the maximum jump at the output, the magnitude of the maximum jump at the output will be the same as the magnitude of the jump at the input, voltage jump at the input. So that's how we interpret this waveform. So when you look at this waveform, you know, okay, it's behaving like a lossy differentiator. So again, I'm using the word lossy differentiator. So when you have this pole, it's a lossy, it's just called a lossy differentiator because ideal differentiator would have given me an infinite output. Okay, but here I'm getting a finite output, and that is dictated by the infinite frequency gain of the system. Now the second case, once you have understood this, the second case that we can analyze is what happens when your time period is much smaller than the RC time constant. Okay, so I don't even get any time to charge the capacitor. The capacitor doesn't, if you're not even giving any time to charge this capacitor. So how does the waveform look like? So I'm applying a sudden step, which let's say it goes from 0 to V peak. At t equal to 0, this node voltage will instantaneously go to, what will the value it will go to? It will go to plus V peak. Then the resistor now will slowly start drawing current and the capacitor will be charged. But because your time constant is so small, you can almost treat it like a linear discharge. Very slowly discharging, almost a linear, because you are, so remember, a first order charging or discharging will be very small. It will be, your capacitor will be slowly charged. So it will be like a very, very slow discharge, linear discharge. Okay. If you plot this waveform, it will be something like Vp into 1 minus T upon tau. So this is a linear discharge, right? So it's 1 minus e power minus T by tau. I'm approximating it to this here. 1 plus, you will get some plus term. So let's ignore that. It will be just a linear discharging. Now, when the falling edge comes, suddenly the input goes to 0. Let's assume this node voltage is some Vp minus delta. What will be the voltage at t equal to T by 2? The capacitor has charged to just delta V. No. At t equal to T by 2, your input signal has gone to 0. And your capacitor has been charged to a voltage of plus delta. It has been charged to a voltage of plus delta. So it will be minus delta. The voltage across the capacitor will be minus delta. And it will again start going like this. Is that fine? Yeah. So it is 0, but there is already a charge stored in the capacitor of value delta. So it will be minus delta. Slowly, what would happen slowly in the steady state is that, what do you think will happen to the voltage across the capacitor, steady state? If I were to ask you, so the voltage is falling from Vp minus delta to minus delta. So what is the step change? This step change is how much? Minus V peak. Yeah, it is minus V peak, right? The step change is just minus V peak. So keep this in mind. In the next cycle, the capacitor will lose some charge. Again, it will start gaining, once Vp comes, again, it will start gaining some charge. Okay, Vp is constantly charging, and again, it slowly loses charge. Just use some intuitions and tell me, can you tell me, this is just a resistor and capacitor in series. What do you think will be the steady state charge across the capacitor? Voltage across the capacitor, steady state. They are just R and C in series. Okay, steady state. No, think like this. I have R and C in series. I don't really care about whether I'm, see, if I take my output across the capacitor, I get low pass filter. If I take my output across the resistor, I get high pass filter. So they both are R and C in series. So I'm asking you, if I feed a pulse signal like this, which goes from 0 to V peak with a time period of T by 2 and T by 2, what will be the steady state DC value across the capacitor? Yeah, one of you got it right. But yeah, I'm thinking, just think, it's just an RC circuit in series. And I'm feeding a pulse signal, which goes from 0 to V peak. On time is T by 2, off time is T by 2. Is that fine? Is it convincing that the capacitor voltage will go to V peak by 2? So every cycle, you will be charging. See here, the capacitor is charged to V peak delta. And in this cycle, again, it will be charged to delta. Every cycle, it will be charged. And then eventually, the capacitor will store a voltage of V peak by 2. Now, let me use this condition. The condition that I'm going to say, your time period is much smaller, okay, compared to this. So eventually, the capacitor will reach a voltage of V peak by 2. But keep in mind, every time you have a step change in the input, what can I say about the step change in the output? At every rising edge and every falling edge, what can you say about the output? Let's talk about just the rising edge. Whenever the input signal goes from 0 to V peak, that's like an infinite frequency input. What will be the change in the output? The same as plus Vp. You should see a same change of plus Vp at the output too. That is that follows from infinite frequency gain equal to 1. This is the kind of, and similarly in the positive negative half cycle, the change will again be minus V peak. So what you will observe is that the waveform will look like this. This is Vp by 2. So if I look at the output signal, it will look like V naught is equal to Vi minus Vp by 2. Okay? Because capacitor is storing a charge voltage of Vp by 2. And I can say that output voltage is simply Vi minus the voltage across the capacitor, which is Vp by 2. What operation is this? What am I doing here? What kind of an operation is this? V naught equals Vi minus V. What am I doing here to the input signal? Does it remind you of any operation? Input signal minus its DC value. Level shift, or I'm removing its DC value. Okay? I'm removing the DC value of the signal. Have you seen such a circuit before? I mean, have you used such? I mean, you must have used such circuits before. Can you think of places where you have used such circuits? Most of you have already used it. Because now you are in third year second sem, you've already used such circuits. Where have you used this? AC coupling. So whenever you build amplifiers, right, that's exactly what we do, right? You DC bias your amplifier with some DC bias voltage to some DC bias voltage, and then you AC couple your input signals. Okay? So this, as far as the input signal is concerned, this is like a high pass filter. Whatever be the DC signal in this input signal, The capacitor will store the DC charge, and the voltage at this point, let's assume for the time being, okay, let's call this VB as the DC voltage. The voltage at this point will be VI minus VDC, okay, plus whatever the DC voltage is at this point, plus VB. So we have already used such circuits. So this circuit is like a DC remover. It's removing the DC voltage from the input. Okay. And the output waveform will look like, if you look at the waveform across the capacitor, it will look like a square pulse which goes from minus Vp by 2 to plus Vp by 2. It will just look like a square, almost a near square wave. I mean, ideally, it will be like, there will be some very small variation like this. Okay. But we don't worry about it. So whenever you see a waveform like this, you know that, okay, it's like a DC coupled, you have the AC coupled the circuit. So this is what we call AC coupling. So whenever you are putting a capacitor in your signal path, you're feeding some signal, and then you have put a capacitor in the signal path. So if you feed a high frequency signal here, the output signal will be an AC signal without any DC content. Okay, so that's how we understand high pass filters. So we have seen high pass filters behaving like differentiators and high pass filters behaving like AC couplers. Okay, they are just removing the DC content of the input signal depending on your frequency of the input signal. If the input frequency, if your input frequency F in is much greater than, F in is much smaller than the F bandwidth, for a high pass filter, it will act like a differentiator. It will just do this, It will just do this. It will act like a differentiator. If your input signal is much greater than F bandwidth, it will act like an AC coupler, and that should make sense, right? Why does it make sense? Let's look at the frequency response graph. If you look at the frequency response graph, if your input signal F or F naught is the fundamental frequency, is much greater than F bandwidth, all your input frequencies are going to lie in this region. So F naught, 3F naught, 5F naught, all these frequencies will be in this region. And if you see, the magnitude of this region is 1, which means any sinusoid of frequency greater than F naught will be passed as it is. That signal will just come out as it is. Except DC, because at DC, the gain is 0, right? If you look at this point, I've removed the DC, but I'm passing all the other harmonics. So that's what's happening in a high pass RC circuit. I'm removing all the DC content alone and passing the AC signal. Now I'm calling it AC, but it's the DC remote signal, which oscillates between a negative and positive values. So that's how we interpret an RC circuit. Okay, so I wanted to discuss integrators, but I think keeping this in mind, I'll start discussing practical integrators. We'll probably spend 1 or 2 lectures on understanding the behavior of integrators to pulse inputs. Okay, so this I already discussed this in my lecture series on passive circuits, but since we are going to talk about integrators and differentiators, I just wanted to quickly refresh all this knowledge, so that in the next class, when we start analyzing integrators and differentiators, you will be able to very easily understand how the waveform shapes should look like. Okay, so I'll stop at this point.